Assalamualaikum warahmatullahi wabarakatuh and very good day. Today I'm going to present a research entitled Indoor Radon Concentrations for Buildings of Different Ages in University of Indonesia. This particular study is related to indoor air pollution as well as radon concentrations. Basically, radon has been recognized as one of the most common pollutants indoors by organizations such as Environmental Protection Agency, known as EPA, and World Health Organizations, which is WHO. Radon does not usually pose as a health concern in outdoor environments, given its high dilution rates in the open air. Nevertheless, hazardous levels of radon can occur within indoor spaces such as basement, bedrooms, office, and houses, especially as it enters via openings in damaged pipes, floor wall joints, or grounds, or via crack in the concrete floor and walls. In recent years, radon gas has been classified as a common radioactive substance to which humans are usually exposed. Radon is a radioactive noble gas without color, odor, and taste that form naturally in the atmosphere due to the decay of radium, thoriums, and uraniums in rock, soils, and groundwater. And prolonged exposure to radon gas is the second root cause of lung cancer among smokers and non-smokers, and hence a significant health threat to public. In both West and East Malaysia, many research groups and professionals have participated in estimations of radon level in various samples, including indoor and outdoor air, building materials, water source, and soil. Radon concentration across University of Indonesia has remained a potential risk of health concern because of the all facilities on campus that may contribute to the generation of the radon gas. Therefore, this particular study is conducted to compare the radon levels between the old buildings and the new buildings of UTM, and this particular study also focused to compare concentrations of radon between ground floor and the second floor within these two types of buildings. To conduct this particular study, University of Indonesia is selected as a study area. A cross-sectional comparative study was carried out inside the old and new building across the Faculty of Science and the Faculty of Civil Engineering, respectively, at two different areas. The target of the buildings of this study include two blocks of Physics Department, Faculty of Science, which named as C21 and C22. Meanwhile, the selected new building for this study is located at Faculty of Civil Engineering, which known as M50 block. The Physics Department and M50 building have been open since 1998 and 2013 respectively. The radon test sites were mainly based in the laboratories on the ground floor and meeting rooms and lecture rooms on the second floor in those three buildings. The duration of this study took around 10 days from mid of August 2020 until end of August 2020. Meanwhile, for the selections of measurement equipment, the RAD7 radon detector from Zurich was used as a primary measurement device in this study due to its versatility and exclusive feature. Basically, in this particular study, the RAD7 was set to measure the mean radon concentration of each spot for 1.5 hours, with the reading recorded in printed copies and the software simultaneously every 30 minutes. Okay, next one, we're going to go for the result and discussion part. Figure shown in this particular slide basically presents the radon levels at C21 and C22, which are the targeted old buildings at UTM. The concentrations of radon varied from one location to another, thus exhibiting distinct readings at the different levels of the buildings. On average, radon levels of the nuclear laboratory on the ground floor C22 were slightly higher than those of the meeting rooms on second floor by 3.8 becquerel. On the other hand, the laboratory contained 9.7 becquerel less radon gas than the lecture rooms on the second floor at C21 in the Faculty of Science. Of all the old buildings included in this particular study, as shown in this particular figure, the radon contents of this location did not exceed the WHO reference levels of 100 becquerel. It has been considered that the building occupants were experiencing low radon exposure, particularly at the nuclear laboratory and meeting room within C22 with concentrations below 20 becquerel. As proven by the previous research, radon gas largely come from the soil, which is this explains the higher concentrations of radon in the nuclear laboratory on the ground floor than inside the meeting rooms on the second floor in the old buildings. However, a different scenario was observed inside the lecture rooms on the second floor in C21, where its radon level was unexpectedly 22% higher than in the nuclear laboratory. These unusual situations could be due to the presence of natural aerosol, which refer to the dust particle with a size of smaller than 0.4.5 micrometer, which arising from the carpet in the monitor lecture room. The radon produced, which then attached to the dust particles of the unclean carpet and accumulated within the room, which contribute to the high concentrations of radon in the lecture room. The second figure that shown in this particular slide indicates the total radon levels of the structure laboratory, meeting rooms and lecture room within M50, which represents the new buildings in UTM. By comparing the concentration of these three locations, perhaps mitigation measure can be recommended as we want to reduce the exposure of those building occupants. It will be good if we are able to decrease the radon concentrations at M50 block as lower as what we have in C21 and C22, which represent the old building. The overall radon levels at the structure laboratory on the ground floor of M50 block in Faculty of Civil Engineering were already lower than those of the meeting rooms by 5.2 becquerel, but higher than those of the lecture room by 35.9 becquerel as illustrated in this particular figure. Similarly, the radon contents of this location inside this new building, similar to the old building, they still not exceed the WHO reference radon level, which is 100 becquerel. Although indoor radons of the lecture room does not pose a significant health threat to the building occupant, both the structure laboratory and the meeting room demonstrate exceptionally high readings despite newer constructions, material, and younger building age. And on the other hand, the structure laboratory on the ground floor show higher levels of radon than those inside the lecture rooms, but lower levels than those of the meeting rooms at the new buildings. It has been anticipated that radon gas in regularly occupied space, for example, in this case, the lecture rooms on the second floor, is often present at lower concentration. Nevertheless, the observations in the meeting room was contradictory to the findings of the past research by Key, with 6% higher radon content than of the structure laboratory. The slight increase in the radon levels of the meeting room perhaps attributed to the formations of cracks and opening on its concrete walls through which radon able to seep through. Based on our observation, there's a formation of cracks and opening in this particular meeting room. That's why we assume that the higher concentration of radon level in meeting room is due to this particular existing of cracks and opening. The lecture rooms in M50 was found to have 75% less radon concentration than ground floor due to the better appearance of material surface. This figure illustrates the comparisons of radon concentrations between the old and new buildings at UTM. Initially, the indoor space of the new building would be assumed to have less emissions of radon gas as compared to the old buildings. If the new building records higher readings, then physical conditions such as building materials or perhaps the ventilation may be the contributing factors or the key factors in this particular case. Unexpectedly, okay, as we can see from this particular figure, radon levels at the laboratory and the meeting room inside M50 were substantially higher than those at C22 by 24.4 becquerel and 33.4 becquerel, respectively. Nevertheless, the lecture rooms of M50 exhibit markedly lower radon content than C21, with difference of 21.2 becquerel. The new building had shown an average of 31.5 becquerel indoor radons, whereas the mean concentrations of radon indoor within the old buildings were around 19.3 becquerel. Okay. When comparing radon levels between the monitored old and new buildings at UTM, the new laboratory at M50 was shown to have 41.4% higher radon than the old laboratory at C22. Similarly, the new meeting room inside M50 manifests 55.2% more radon content than its counterpart at C22. However, the radon concentration inside the lecture rooms at C21 was significantly greater than M50 by 65.2%. Basically, the observation coincide with the findings by a researcher named Ko that the ventilation rate indoors play a key role in variations of radon concentrations, and we believe that the ventilation factor is the one who actually contribute to the higher concentration of radon at the new building. Contemporary and newly developed buildings basically are more energy efficient and airtight, thus preventing additional energy costs as well as the entry of air from outside if the indoor space is air conditioned. Nevertheless, the air exchange between the outdoor and the indoor is less likely to occur in the modern buildings, especially when the aircon or air conditioner are turned off. And we believe that this justify the greater concentrations of radon within the indoor space of the new buildings in comparison with the old buildings. Conversely, the old buildings may have ventilation systems that allow the outside air to enter and leave efficiently after mixing with the air indoor on a timely basis. Represent the comparisons of radon concentrations between the ground floor and the second floor for both buildings, the old one and the new ones in UTM. In comparison, as we can see from this particular figure, radon levels on the ground floor of C22 were slightly lower than those of the second floor by 8%. Meanwhile, the ground floor of M50 demonstrated 22.5% higher radon content than compared to the second floor. In general, okay, radon level in both old and new buildings were all below the WHO reference level, which is 100 becquerel. The health risks of the student and staff from radon exposure in the monitored indoor environment were presumably low and insignificant. Although both types of bidding demonstrated concentration that were well within the limit value that established by WHO, it was noteworthy to know that no threshold level has been set by any internationally recognizable organizations, and even a small amount of radon may be associated with certain health issues, particularly related to lung cancer. Therefore, it would be ideal to suggest some mitigation measure in this study to attain near zero exposure to radon within interior of the old and new buildings at UTM. As for conclusions, the radon concentration inside the locations of the old buildings were all below 30 becquerel, whereas those inside the new buildings were below 50 becquerel. Hence, they did not exceed the WHO radon reference level of 100 becquerel. At the old buildings, radon levels of the nuclear laboratory on the ground floor were slightly higher than those of the meeting rooms on the second floor. Nevertheless, the laboratory contained less radon gas than the lecture rooms on second floor. This could be due to the presence of natural aerosol that attached to the dust particles of the unclean carpet and accumulated within the rooms. But on contrary, the structure laboratory at the new building on the ground floor had a higher radon level than those of the lecture rooms, but lower readings than the meeting room on the second floor. The slight increase in the radon levels of the meeting room was attributed to the formation of cracks and opening on its concrete walls through which radon gas able to seep. The air exchange between the outdoor and indoor is less likely to occur in in the modern buildings when air conditioners are turned off, and conversely, the old building may have a good ventilation system that allow the outside air to enter and leave efficiently and able to mix with the air indoors on a timely basis. Okay, that's all from me. Thank you so much for listening.